So today I will talk about the principal component analysis or the empirical orthogonal function which we use in meteorology uh, number of times. For example, sea surface temperature anomaly. We see a spatial pattern in latitudes and longitudes. Uh, the sea surface temperature anomaly, for example, in the EOF1 we see that in the Eastern Pacific some positive anomalies, in the Western Pacific having some negative anomalies, and so on. There are many EOF modes which we see, and we also see another important thing, which is the percentage of variance captured. This is also which we see quite often, that what is the meaning of this percentage of variance captured, what is actually this EOF, and what is the principal component analysis. What are those? What are the PC time series which we say? So generally we talk about this EOF pattern plus the PC time series in the meteorological data. So we will see that what are those particular things in a very simple mathematical uh, framework. The mathematics behind that I will derive here, and from there we will understand that what mathematical expression is actually is UF, and what mathematical expression is nothing but this PC time series, and how this percentage of variance captured is calculated. So for that, first of all, this principal component analysis, what I have written here, is nothing but a dimensionality reduction technique. We all know this, that it's a dimensionality reduction technique. So it's a dimensionality reduction technique. How it is reducing the dimension, we will see very soon. And it also follows the orthogonality. Orthogonality in linear algebra is a very important aspect, that some A transpose A is equal to I is equal to A transpose. That means that particular matrix is orthogonal. Okay. So now let us consider that there are two vectors, say x1 and x2. Okay. So this x1 vector is having x11, x21, and so on up to xn1. So there are n elements in x1 vector and n elements in x2 vector. So 1, 2, 2, 2, and so on up to xn2. So this is your x1 and x2 vectors. Now, if we draw a graph, which we generally see in a principal component, any lecture in the principal component has this particular graph, that you have x1 and x2 scatter plot. If you make, then most of your points are lying over this particular area, and some definitely deviations are there. So points are here and there, and it is placed over these particular regions. Okay. Now, if we see what is the variance in the x1 direction, it is this, isn't it? So this is the variance in the x1 directions. And what is the variance in the x2 direction? So this is the variance in the x2 direction. So we can see that the variance of x1 is comparable to the variance of x2. So no dimension can be neglected here. But instead, if we make our coordinate system somewhat different, let us consider that this is our coordinate system. So this is my Z1, and its mutually perpendicular thing is Z2. Okay. So now if I write this particular thing, say Z2 is this and Z1 is this. So we can see that most of the points are lying over these regions, right? So all the points scattering things is now here. Let us write this is Z1 and this is Z2. So now the percentage of variance explained in Z1 is this, but the percentage explained in variance in Z2 is this. So this is variance of Z2, this is variance of Z1. So earlier what we have seen that it is comparable, this x1 and x2, but variance of Z1 is much greater than variance of Z2. Now we can reduce a dimension. So only if we use this particular Z1 direction, maximum variance we get. We don't need to see about the Z2. We only can use the Z1 direction to understand what the variances are, and we can further analyze this particular data. So this is how from 2D to 1D it comes, and hence it's called as a dimensionality reduction technique. So this is the important thing. Now going into the mathematics a little bit, what is actually happening? This x1 and x2 coordinate system, I have rotated it anti-clockwise with an angle theta, right? Then only these z1 and z2 coordinates came, and this in between z1 and z2, there is a 90-degree angle. Obviously, x1 and x2 also has 90 degrees, so this is the thing. And we know that z1 and z2 can be written mathematically as cz1 is equal to x1 cos theta plus x2 sine theta. You can see it very carefully. If you see this particular figure, you can understand what I am writing. And similarly, z2 will be equal to minus x1 sine theta and x2 cos theta. Right, and in the matrix form, we can write it like this. So this is z1, this is z2, and this is your cos theta, sine theta, minus sine theta, and cos theta. Correct? And we can write it like x1 and x2. Remember, the z1 and z2 are the vectors. X1 and x2 are the vectors. It consists of n elements, and this is a particular matrix. Okay, so these are nothing but your PCs, the principal components, which I have shown here. These are nothing but the principal components because it's the dimensionality reducted thing from where we can get that the variance of one dimension is much more than the variance on the other. So we can neglect another dimension and only go towards the particular maximum variance captured dimensions. That's all. These are the PCs. Now, if we go for say more higher dimension, then what we will get? Say suppose uh, yeah. So suppose now z, instead of two vectors, we have p vectors. So z1, z2, and so on up to p vectors. So zp. Okay, each consists of n elements. So this is now actually 2 by n now. This is 2 by 2 now, and this is 2 by n. Okay. So this will be now this will be what? Then it will be a11, a12, and so on up to a1p. This you can go AP1, so on up to APP. These are all constants. These are all constants like this. For p dimension, it will be somewhat different. And this will be x1, x2, and so on up to xp. Right? Now what I can write is that z is now, it is p by n is equal. This I am writing it as A transpose p by p. And this I am writing as, again, p by n. So left hand side and right hand side dimensions are matching. So this is the expression for the p rows or p vectors with each vector consists of n elements. This is a covariance matrix kind of thing. So it's A transpose and x p by p, p by n. So what is this A transpose? Will come very soon. We will come. Now again, if we go to the what do we call as two dimension? Again, going to two dimension. One important property I have to show. Again, going to 2D. What I get is, if you go to this A transpose, it becomes A transpose will be equal to what? Cos theta sine theta in two dimension I'm talking about. And it is minus sine theta cos theta, isn't it? So now okay, I have used here A transpose, you can use A. Only thing is that things will change. There will be no difference. You can use A transpose instead of A. It is absolutely fine. There is no problem. And A will be therefore just changing the rows and columns. So cos theta it will be minus sine theta. This will be minus sine theta. It will be sine theta. This will be cos theta. Correct? Now, if you do this A into A transpose or A transpose A, you will definitely get this particular product as 1001 because these diagonal elements you will get cos square theta plus sin square theta, which is 1. So this is an identity matrix. But what is this important property tells you? This is nothing but the orthogonality. That's why I'm talking about the orthogonality condition is satisfied. This is very important. Okay. So orthogonality condition is satisfied or orthonormality condition is satisfied. Okay. So now going back to this particular thing, let us write one of the vectors, say jth vector, zj, can be written as a j1 x1 plus a j2 x2 and so on up to a j p xp. Why am I writing? Because it is p by n. So we can write it like this, isn't it? Yeah. So each of these x1 is having this 1 by n. So these are all n elements we have. Okay. So writing it in this now, AJ, sorry, this is transpose are always there, so nothing to worry about. So it will be AJ transpose into X, right? ZJ is equal to AJ transpose into X. So what you have here is 1 by N or let us consider this. Oh, fine. So this is 1 by N, this is 1 by P, and this is P by N, right? This we can write because this is one of the vectors. This is one of the vectors. So one of the vectors means each vector is having 1 by n. So that's why this is the thing. Aj is 1 by aj. All these aj's are nothing but 1 by p because I am writing one of the rows. So 1 by p, and this is the p by n. The x, original x will always be there. Okay, so we can write it like this. Now let us find out what is the covariance of zj. What is the covariance of ZJ? Since we are talking about how much variance, we are talking about some maximum variance condition in the principal components. So we want to know that each principal component, Z's are nothing but the principal components. I have already shown that with the diagrams. In the above figure, I have already shown that this Z1 and Z2 are the principal components. Okay, so I want to see what is the covariance of ZJ. For that, what we will do? This will be nothing but what? Covariance of AJ transpose X. No problem in this. Now, what is the definition of covariance of X? So covariance of X comma X. Actually, it is covariance of Zj comma Zj. That is nothing but E of, in the matrix algebra, it will be written as X minus mu X into X minus mu X transpose. Because we are dealing with matrix. But if we are dealing in the entire statistics, this transpose will not come. It will be X minus mu X into X minus mu X. That's all. So covariance of Zj. Again, if we come, what it comes out to be, it will be expectation value of, write it very carefully, AJ transpose X minus exponential, because this is not, it's not the exponential, this is the expectation value. So it is E of X. This mu X is nothing but E of X in the statistics. So expectation value of AJ transpose X, okay, minus AJ transpose X, AJ transpose X minus, again, expectation value of AJ transpose X and whole things transpose and then bracket. Okay, coming back to the next step, AJ transpose. These are all constants, so we can take out. So AJ transpose, I am taking it common. Let us put the expectation here, and it will be X minus E of X. Correct? Minus. AJ transpose, I am taking common from here also. So it will be X minus E of, again, AJ transpose can be taken common. There is no problem in this because it's all are constant, and entire transpose and then this. Therefore, AJ transpose can be taken common here. So expectation of X minus E of X minus A into B whole transpose is B transpose A transpose. So this is suppose A and this is suppose B. So AB whole transpose is B transpose A transpose. So we can write it as Oh, sorry. This extra minus sign from where I have taken, I don't know. This should not be there. This is a multiplication. There is no minus sign is here. Okay. So, oh, wait. No minus sign is there. It's only just the multiplication. Hmm. Okay. So what I will have is this x minus e of x, this transpose into aj, because transpose will be aj. Okay. This thing will come. And aj is a constant. In the next step, we can remove it outside. So it will be nothing but x minus e of x, okay, into x minus e of x transpose rotation h. So what we are getting is that, let's change the color again. What we are getting, therefore, its covariance of zj is nothing but aj transpose covariance of x and h. This is actually the covariance matrix. We call this as covariance matrix and denote it as S. So this is nothing but AJ transpose SAJ. This is the covariance of ZJ. So this thing is clear. Okay. Now this we have got. Now what is this thing is that this is nothing but representing some variance kind of thing. And what we have to know is that first, so suppose there is a complete set. So space is there, universal space is there, in which this amount is Z1, this amount is Z2, and slowly it is reducing, and so on. Okay. So this is how it is made. So what we need to do is that covariance of Z1, certain conditions we need to follow. The covariance of Z1 first is maximum. That is, Z1 is capturing maximum variances, and it should also follow the condition that A1 transpose A1, this particular things, is also equal to 1, the orthogonality. These are the two conditions. I have already told you that these are the two conditions which we will use to understand the principal components. Orthogonality should be followed and the covariance should be maximum first. Second thing is that after this thing is done, after these conditions is satisfied, we will go to the covariance of Z2. So out of the remaining now, Z1 is done. Out of remaining, covariance of Z2 should be maximum, and A2 transpose A2 is equal to 1. And in this way we will proceed. This we will proceed. That's all. Now, to understand this condition of maximum, so let us consider that covariance of Zj needs to be maximized, should be maximum, and and a constraint is there. A constraint is also there. That is what? Aj transpose Aj should be equal to 1. This is for the jth vector. This is for the jth vector. Okay, this is for the jth vector we are talking about. Now, this maximizing thing, I will do it using Lagrangian multiplier. So, using Lagrangian multiplier, I will try to demonstrate how this maximization is done. So, my Lagrangian will be, actually, the general formula is this. This is the general formula for the Lagrangian. That is, it should be f of x minus lambda times constant. Lambda is some constant. Okay. So, f of x is nothing but the covariance of zj, which we are talking about, minus lambda times this thing can be written as aj transpose aj minus 1 is equal to 0. So this equation needs to be put it here. So aj transpose aj minus 1. This is my Lagrangian, and this becomes nothing but aj transpose aj. Oh, sorry, there is a f also here. Yeah, minus lambda aj transpose aj minus 1. Now, if you do maximizing this Lagrangian with respect to delta Aj, Why? Because for what value of AJ this Lagrangian is maximized. So this should be equal to 0. Any maximum minimum condition, this should be equal to 0. So ultimately, if you differentiate it, it comes out to be 2AJS minus 2 lambda AJ should be equal to 0. So ultimately, we get S minus lambda I AJ is equal to 0. And this gives very interesting expression which we generally use in the matrix algebra. It's the eigenvalues and eigenvectors. This is this. So it is quite similar to what we follow, that AX is equal to lambda X, where A is some matrix. In this case, it is covariance matrix. These are the X, the eigenvectors. Okay, and these lambda are the eigenvalues. Here also we will say the same thing. S is the covariance matrix now. Covariance matrix. AJ is the eigenvectors. And lambda is nothing but the eigenvalues. Remember, this lambda j which I am writing is for the jth eigenvector. This is the eigenvalue. This is one value only. This is not a vector. Okay. So this is what we have got. Enough of mathematics now. We will try to understand with an example now what we see, that empirical orthogonal function as a some kind of a pattern, like this spatial map which we get in the empirical orthogonal functions, where some spatial maps are there. Somewhere it is positive, somewhere it is negative. What does that indicate? And what we get is a PC time series, some kind of time series we get. So this PC is also, we want to find out what one is this EOF, another is this PCs. What are these? From these, actually we have got two mathematical expressions. So what are those things we need to understand? So by changing the color, first equation which we have got is, say, this one, S AJ is equal to lambda AJ. The second equation what we have got is ZJ is equal to AJ transpose into X. Okay. So now for the EOF, let us consider that EOF and PCs we will see. So let us consider that example. Let us take an example. So we have been given that sea surface temperature anomaly data, which is having 400 space points, or 400 space points and 100 time points. 400 space points consists of 40 lakhs into 10 lons. This is the time. Okay, so this kind of a data is being given. So this is the space dimension and 100 is the time dimension. Okay, fine. So now this, I will say this is equivalent to our X, which we have here. So X is P by N. So P is 400, N is 100. Okay, now everything is now being understood properly. Okay, now let us consider the first equation. Okay. What is the first equation? Tells S AJ is equal to lambda AJ. Now, okay, I know already. I know that this AJ transpose is having 1 by P as the, so already I know that AJ transpose, I have already shown it somewhere. Where is it? Where is it? Where is it? Yeah, no, not here. Here. Uh, yeah, this AJ transpose, see, this is 1 by P. So AJ will be what? Therefore, it will be P by 1, right? So it will be P by 1. So AJ will be P by 1. Dimension, the P by 1. This is also P by 1. Now to have this S, which is a covariance matrix, and it's a, yeah, and it's a square matrix, so it has to be P by P. Nothing can be there without this. So it has to be P by P. Then only this condition is satisfied. So this is P by 1, this is also P by 1, because lambda is a constant value. Okay, this is the eigenvalue. Now here we can see that EOF is a special map. No time is included here. See, where is the special thing? This is nothing but the EOF. This we call as the EOF, the empirical orthogonal function, which are nothing but the eigenvectors. Eigenvectors of this particular expression are nothing but the EOFs. This is for the jth EOF. So this is the jth EOF mode. Okay. S is nothing but the covariance matrix of what? Covariance matrix of what? We have already shown this covariance matrix of X. X is what? Of X. X is what now here? Surface temperature anomaly. So whatever the sea surface temperature anomaly I have, its corresponding covariance matrix, if we calculate, then we get S as P by P. And the AJ which we have got is the jth eigen, your EOF, the empirical orthogonal function, is lambda. This lambda is the eigenvalue corresponding to jth UF. Correct? This is done. So we have seen now the mathematical expressions which we have got, say equation 1 and equation 2, which we have derived from this first equation I am using, and we have already seen what is the empirical orthogonal function, what are the covariance matrix, and what is this lambda represents. Now comes the percentage of variance experiment, because if you see a map here, EOF captures certain percentage of variance. How to calculate this? How to calculate this percentage of variance? Let us see. So percentage of variance captured by jth mode, jth EOF mode is given by lambda j divided by summation of lambda j, j going from 1 to space dimension p into 100. That's all. Therefore, for EOF1, we have lambda 1 divided by lambda 1 plus lambda 2 and so on up to how many? Lambda p into 100%. Similarly, UF2 is same, lambda 2 divided by lambda 1 plus lambda 2, so on up to lambda p into 100%. And it goes so on and so forth. Okay. So this is what we have got, the empirical orthogonal functions. And we know that PCs, the principal time component time series, what we say, these PCs I have already shown that this is Zj, nothing but Zj. And that is nothing but we have got AJ transpose into X. Equation 2, right? Equation 2. Zg is equal to AJ transpose into X. And we have also seen that the dimension is 1 by n. It should be, because n is nothing but representing the time. N is representing the time. P is representing the space. So we call it as a PC time series. So it's true that it is a time series because it is of 1 by n in this example. And AJ transpose will be what? 1 by P, because AJ is P by 1. X is what? P by n. The format of sea surface temperature anomaly. So this is the PCs of jth PC. This is the transpose of jth EOF mode, and this is nothing but sea surface temperature anomaly data. So this is how this time series. So this is the time series which we see in the PC time series. We call something it denotes. So these are the PC1, suppose, and this is time. And these are the EOFs. Say for EOF1, some special thing, some positive anomaly, somewhere negative anomaly, somewhere positive anomaly in the space, polar space. Okay. So these are the thing, and percentage capturing is this. And how this percentage is, so lambda 1 will be maximum because we have seen that this particular thing, that covariance of Z1 is first, it's maximum, then it goes like this, right? What we have seen here also, you can see this particular thing. See, variance of Z1 is much greater than variance of Z2, and similar thing happens here also. What happens is that covariance of Z1 is much greater than covariance of Z2 is greater than covariance of Z3, and so on and so on. Okay, so this is what it happens, and ultimately the lambda ones are changed like this, and the percentage of covariance goes decreases like this with the mode. So this is the percentage captured, and this is NEOF, the modes. So we have understood that what is the mathematical background, very basic mathematical background behind these principal components and the empirical orthogonal functions, and we have maximized using Lagrangian multiplier here. And finally, we have seen that these two expressions are very important to understand the PCs and the EOF and to relate it properly. And we have seen that from the first equation, S is the covariance matrix from of this sea surface temperature anomaly. Ages are the nothing but this what we call as the empirical orthogonal functions, which shows the pattern, and then lambda are the eigenvalues, which helps us to calculate the percentage of the variance captured. If you know this EOF and the temp data is already given to you, if you know this EOF from the first equation, you can put it, its transpose times the sea surface temperature anomaly data will give you the PC for that particular component. So this is the background behind what we call as the PC time series in the meteorological data and the EOF analysis, what we call the empirical orthogonal functions, the space-time map, the spatial map, which we see for sea surface temperature anomaly or rainfall, something like that, is this particular concept.